Okay, so we've been talking about bases. Now we're going to talk about a particular type of basis called orthonormal basis. Now let me take you back when we first started talking about orthonormal. If you remember, we talked about orthogonality. Orthogonality came through an inner product. When we have two vectors whose inner product is 0, those are called orthogonal vectors. We also got this Gram-Schmidt procedure that allowed us to create a linearly independent set of orthogonal vectors. So remember this theorem. This theorem says that if you have a linearly independent set, through a certain process, you can create an orthogonal set of vectors that's also linearly independent and has the same span. And one further step that we did was turn these orthogonal vectors into orthonormal vectors by dividing each vector by its norm. So here was an example. You had 3 vectors and you divided and you computed the norm of each vector and you divided each vector by its norm to get an orthonormal set of vectors here, here, here. Okay, so we're going to do something. We're gonna run with this a little bit and look at the orthonormal. Let's see. Right. So now really what we've already done is talk about basis, because we have an orthonormal linearly independent set. So this in fact is a basis. Okay. Now another thing that we looked at before were unitary matrices, and you can look back at that definition. Okay. A unitary matrix is one whose adjoint is its inverse. Okay. We had self-adjoint matrix was a matrix whose adjoint was itself. We all have unitary matrix as a matrix whose adjoint is its inverse. One of the theorems that was proven in this section was that columns of unitary matrices are orthonormal sets. Okay. We also have a theorem that says that orthonormal or orthogonal vectors are linearly independent. So in fact, the columns of a unitary matrix also form a basis, and this basis of vectors these vectors are orthonormal. Okay. So what we're going to talk about in this section really has precedence in these 2 previous sections. Okay, so let's go back. All right, so just remember, we've talked about orthonormal vectors. We use the Gram-Schmidt procedure to create orthonormal vectors. We also know that unitary matrices, the columns of unitary matrices, are orthonormal, so they'll be an orthonormal basis. And in fact, the columns of an n by n unitary matrix form an orthonormal basis for Cn. Okay, so why are orthonormal bases so nice? Well, we've been using basis or linearly independent sets to express vectors as a linear combination. And if you have an orthonormal basis, it's particularly easy to find the linear combination required. Now, there is a general method for expressing an arbitrary vector as a linear combination of orthonormal vectors, and that general method is expressed in this theorem. But before doing the theorem, let me show you how it works in a particular case. Okay. All right, now suppose we have a vector W given by this, and we want to express that as a linear combination of an orthonormal set of basis vectors. All right, so here's an orthonormal set of basis vectors. All right, this was obtained using the Gram-Schmidt process and then converting to orthonormal set. Where it came from is not important. The important thing is that this is an orthonormal set, which you can verify. You can verify that the norm of each vector is 1 and that the inner product between any 2 vectors is 0. Okay, so the problem at hand is express this W as a linear combination of these three vectors. Well, the way you do it is you take the inner product of W with each one of these vectors in turn. Now, unfortunately, there's a slight misprint here. When the vectors are real, it doesn't matter, but this really should be V1 inner product with W. This should be V2 inner product with W. And this should be V3 inner product with W. Okay. All right. So as I said, when the vectors are real, this doesn't make any difference. If they're complex, then you get complex conjugates. Okay. So if I take this inner product, let's verify that V1W is 5 over square root of 6. Well, W is here, so here I'm going to have 2 times 1, which is 2, plus minus 1 times 2, which gives me 0, plus 5 times 1, which gives me 5, all over square root of 6. So the inner product is 5 over square root of 6. You can verify these other inner products as well. And these inner products are exactly the coefficients I need in the linear combination. Now, that's not something that's obvious. That's something that we'll be showing shortly. But that's the nice thing about orthonormal vectors, is if you have an orthonormal set of vectors, and you want to express another vector in terms of those, all you have to do is take the inner products, and they give you the coefficients. Okay? Now, there's a slightly more complicated example up here. Well, not slightly, but somewhat more complicated example up here. Suppose we have a set of vectors here. Turns out that these vectors are orthogonal. It was verified before. To make an orthonormal set, you need to divide each vector by its length. Okay? Remember how you compute length is you're going to take the inner product of the vector with itself and then take the square root. Let's just verify this one here, that the norm of x1 is square root of 6. So norm of x1 is equal to the square root of the inner product of x1 with itself. Now, if I take the inner product, remember when you take the inner product, you're going to take the complex conjugate, which is 1 minus I, times 1 plus I. And then here I'm going to take plus 1 times its complex conjugate, which is just 1, plus the complex conjugate of 1 minus I, which is 1 plus I, times 1 minus I. And then plus, I'm going to have the complex conjugate of I, which is minus I, times I. And I take this to the 1/2. Okay, so if I do this, I'm going to use this formula that A minus BI times A plus BI is equal to A squared plus B squared. Very handy formula. All right, so here I have my A is 1, my B is 1, so this is going to give me 1 squared plus 1 squared, which is 2. This is going to give me 1. This is going to give me another 2, and this is going to give me 1. So you can see I have 6 square root of 6, so that gives me the square root of 6. All right, so that was just a side note to show how you do compute the norms of these vectors. All right, so I take this orthogonal set, I create an orthonormal set by dividing by the norms. So here's an orthonormal set of vectors. So we're facing this problem. By the way, we know that this orthonormal set is a basis for C4 because these if I make these as columns of a 4x4 matrix, and I know that they're linearly independent, so we know the columns form a basis for C4. So I can write any vector in C4 as a linear combination of these 4. How do you get the linear combination? Well, you take the inner product of this vector with each of the 4 vectors in turn. Now, unfortunately, this is backwards. It should be V1 with W. This should be V2 with W. This one should be V4 with W. And this one should be V3 with W. All right, so you have these four inner products. So in fact, we've shown before that if you reverse the order of the vectors, you get the complex conjugate. So that should be a plus. That actually should be a minus. That should be a minus. And this should be a plus. So when you compute these inner products, these turn out to be exactly the coefficients that are required in the linear combination. Okay, so the linear combination of this arbitrary vector is equal to the first inner product times the first vector plus the second inner product times the second vector, which is here, plus the third inner product times the third vector, which is here, plus the fourth inner product, whoops, I'm sorry, got the wrong place, plus the fourth inner product, which is here, and that should be a minus, times the fourth vector, which is here. Okay. So it's kind of messy here, but just please make the connections here. You take the inner product, you take the inner product which goes with the corresponding vector, and you create that term, and you're going to get four terms altogether. Okay, so that's the procedure. Take your orthonormal set, take the four inner products, make sure you have the order correctly. You take the basis vector first, and then the arbitrary vector second. And that gives you a linear combination that gives you your arbitrary vector. Okay, so now we've talked about it. Let's go back to the theorem in general and see how this works. So here's what the theorem says. Suppose I have a set of P orthonormal vectors. These form an orthonormal basis of a subspace W. Okay, of course, they're going to be an orthonormal basis of their span. So every W that's in this subspace can be written as follows. W equals inner product of the first basis vector with W times the first basis vector plus inner product of the second basis vector with W times the second basis vector plus inner product of the third basis vector with W times the third basis vector, etc. Okay. Now, why does this work? Well, if we know that W is in the subspace, we know it can be written as a linear combination. And we can take the inner product of both sides of this equation with each basis vector in turn. So that's what's done here. I take this vector W and I take the inner product with VI, which represents an arbitrary basis vector. Okay, so I'm taking inner product of VI with W, and I'm doing it on this side as well. I'm just expressing this sum in summation notation. Right now, by property of inner products, we know that if we take the inner product of a vector with a sum of vectors, that's just the same as the sum of the inner products. We also know that if we take the inner product of a vector with a scalar multiple of a vector, that's just the scalar multiple of the inner product. So I can take this AK out here. Now look at this inner product VI with VK. If V is an orthonormal set, then this result is either going to be 1 or 0. It's 1 if I equal K, and it's 0 otherwise. So out of these K terms, there's only one term that's non-zero, and that's the term where K is equal to I. Okay, so he separated out this one term where K is equal to I. These are all 0, and I get AI. So this is a way for me to isolate AI simply by taking this inner product. Okay, so that justifies the formula. You can see now that it's much easier to find these coefficients when the vectors are orthonormal. When we didn't have orthonormal vectors, we had to row reduce the matrix whose columns were the column vectors here, and we had to form the augmented matrix and so on. So this is a much easier way of finding coefficients. And I think that's well, no, there's one more thing here. Now, we know that a space can have more than one basis. Okay, we've already seen several bases for Cn. So the question is, can we change from one basis to another? And this theorem talks about some conditions in which we can change from an orthonormal basis to another orthonormal basis. Okay, we know that we can take vectors and multiply them by a matrix. And what this theorem says is, suppose I have an orthonormal basis of Cn, and I multiply each one of these vectors in the basis by a unitary matrix. Okay. Then the result will be a set of n vectors, and these n vectors are also an orthonormal basis. Furthermore, if I have a matrix A that has this property, then A must be a unitary matrix. Okay, so the theorem says if A is an n by n matrix and B is an orthonormal basis, if I take the set of vectors C obtained by multiplying A by each of the vectors in B in turn, then A is unitary if and only if C is an orthonormal basis of Cn. Okay, this has a long proof. It's not really complicated, it's just a lot of notation, but I want to just emphasize the statement here. We'll be using this later, so keep this filed in the back of your mind, and we'll be using this fact later.